Hello and welcome. We're going to be talking about section 12, preparation and reaction of amides. For this video, I don't have a little pop out with my picture talking along, but I'm very much alive and real and here to discuss with you several reactions that amides undergo. Now, when you want to do a hydrolysis of an amide, there is only one possibility. You cannot, I repeat, you cannot hydrolyze an amide with base, okay? This is oftentimes a favorite, question of a professor. Why don't you make the carboxylic acid or the carboxylate and, kick off ammonia? Why does not this occur? Now, the reason why is because amides have a semi-acidic hydrogen here. Okay, so if you have a hydroxide, this will deprotonate like so, and you make a resonance stabilized negatively charged guy. Now, if we draw the negative charge here on the nitrogen, this is less favorable, okay? You remember how when you discuss resonance structures, there are a ranking of the relative importance or contributors to the resonance hybrid, and this guy here on the right would be more contributing because the negative charge is on a more electronegative atom, okay? So when you think, well, I was going to draw the negative again. When you think about this, this is very stable. Okay, these are both, okay, the real resonance structure is somewhere in between these two, but this is negatively charged, okay? So the hydroxide, which is a nucleophile because it's negatively charged, are not going to be attacking these positively charged the electrophile is normally positive, but this is a terrible electrophile because it's negative. So negative and negative repel. So this hydroxide is not going to attack and do additional substitution, okay? So this guy here, actually, there's no reaction. Now, a reaction that you can perform is acid-catalyzed hydrolysis, okay? So let's go back to our guy here. And we're going to be adding H3O plus and heat, okay? So, this is basically H3O plus, just think about it as H plus, which is a catalyst, and water, okay? And this will hydrolyze by adding water to the components here to give you the carboxylic acid and then ammonia. Now, under acid conditions, we're going to actually form ammonium, okay? So let me take you through the curved arrow reaction mechanism and show you what that looks like, and then I'll show you a couple examples, okay? So let's take acetamide here, and we'll just draw H2 here. So in the first step, as usual, when you have acid in your reaction mixture, you want to be protonating something first, okay? Now, normally amines are more basic than, say, alcohols or something like that, but we want to protonate the carbonyl oxygen. Now, the reason why is that you get a resonance stabilized intermediate, okay? So let me draw out the H's now. So, we've got a lone pair next to a pi bond, and there's lots of resonance possibility there. Now we have water present. Okay, so here's where our reaction solvent water is going to engage. Carbonyl carbon. Okay. And we're going to form the super famous tetrahedral intermediate. Now, this is a bad leaving group. Okay, this is a bad leaving group. We want to protonate that nitrogen to expel the neutral leaving group, okay? Now, remember, when you have water as a leaving group, you normally protonate the oxygen. Okay, I'll just put an R group here. And this is going to depart, and neutral water leaves. When you have amines, okay, that are going to be potential leaving groups, you want to protonate, have the positive charge on the nitrogen so that your neutral leaving group can leave. Okay, so that's what we want to do here, especially since we have acid conditions. So we need to do a number of proton transfers. First, we're going to grab water, which is the reaction solvent. Okay, that's going to pluck off this proton here, and via deprotonation, form this guy here. Okay, and remember again, we're operating under acidic conditions, so H plus is our catalyst. Protonate. And now we have a good leaving group poised to depart from this molecule. So I finished drawing all these components here. Okay, so now at this point we can just kick off the leaving group. And recall again that we always want to use lone pairs. You could use lone pairs on this oxygen or the other oxygen if you like. And so here you want to bring them down. Okay, that's going to create a carbonyl and break this carbon-nitrogen bond. Okay, so this is where ammonia comes off. Let's draw this out here. Now, a couple things are going to happen. We have ammonia, which is a base. Let me just label that here. Okay. And we have this protonated carboxylic acid, which is definitely super acidic. Okay. So we want to remove this proton here, and we want to protonate this nitrogen here. Now, these molecules are probably drifting apart in solution, so it's more likely for this nitrogen to pick up a proton from the acid medium reaction mixture to form ammonium. Okay, so this is called ammonium. And this protonated carboxylic acid is more likely to interact with the reaction solvent, which is quite plentiful. And so it meets its end by a deprotonation step. And that gives you, kind of running out of space to draw this, it forms the carboxylic acid. Okay, so the final products from this reaction are going to be your carboxylic acid, okay, and the protonated nitrogen guy, okay? So in this case, we just have a primary amide, so that's going to be ammonium. In cases where you have a more interesting structure, say for example, let's put two methyl groups on here, for example. And so again, if we treat this with H3O plus, and don't forget the heat, okay, the triangle symbol there represents heat, we're going to form the carboxylic acid. So you just need to recall that this is the bond that's being broken as usual. And we're going to form the ammonium, all right? So draw your nitrogen, draw your two methyl groups. Okay, so those are the organic carbon-nitrogen bond containing components. And then you want to draw not one hydrogen, but two hydrogens. Okay, so nitrogen with 4 bonds is always going to have a +1 formal charge. Okay, so that's the products. Okay, so let's identify H2O. We're basically adding hydrogen and an OH, which is H2O. Okay, so H plus is the catalyst. It goes on to catalyze more events. Okay, and so it doesn't really matter what kind of structure you have. Let's do an amide that looks like, I don't know, like this. Okay. So if we again treat this with H3O plus and heat, okay, we want to break this bond here. So on the right-hand portion, you're going to form a carboxylic acid with the correct number of carbon atoms. Okay. And on the left, you're going to form the amine. Now the phenyl group stays attached to the nitrogen. And so you just want to draw 1, 2, 3 hydrogens in order to have 4 total hydrogens, 4 total bonds on the nitrogen. So yeah, that's pretty much what you got to do there. If we take a look now at some other reactions, we can kind of look at what they do, all right? So that's the acid-catalyzed hydrolysis of amides. Okay, I didn't label it here, but that's reaction 1. Reaction 2 is going to be the reduction of amides. Okay. Now for this, I'm not going to show you the curved arrow reaction mechanism because it doesn't follow the general pattern that we have in the organic chemistry reaction of acid halides and acid anhydrides and stuff like that. Normally when you add hydride, you replace this with a hydrogen, okay? And the aldehyde can go on and react, and you end up at the end with a primary, alcohol, okay? Now, in the case of amides, it's very different, okay? So let's make this asterisk even bigger. Watch out for this. If you have an amide, and you treat this with lithium aluminum hydride, which is always excess, okay? You don't form a primary alcohol, you form an amine, okay? And hydride, okay, delivers 2 hydrogen atoms here, okay? So it's a kind of exception to the general rule that we saw for nucleophilic acyl substitution. For my class, don't worry about the mechanism here, okay? As I look through the Klein's organic chemistry textbook, they don't even show it, okay? There is a mechanism, it's quite interesting, but it doesn't kind of follow the general thing that we've memorized for all 10 different reactions that are all exactly the same, okay? So you need to memorize acid-catalyzed hydrolysis. And you need to memorize the reduction of amides. That's it. Those are the only 2 reactions that you can do for amides. Why not anything else? Well, it's because amides are so resonance stabilized that they're just so unreactive. And so lithium aluminum hydride is an extremely reactive hydride reducing agent. And acid catalysis, well, you're thinking, well, it's just acid. But we're talking about extreme amounts of heat, refluxing overnight, a very long, lengthy, very severe reaction conditions to get that to go. So let's do some practice here. I'm looking in the book on problem 26 and 27. So let's see if we can do these. So problem 26 just asks us to draw the products, so no mechanisms necessary here. And so of course when you have an amide, you want to keep all of these carbons in the particular branching. And remember that excess lithium aluminum hydride will make amines. Okay? So you just draw out the NH2 here, And make sure that methyl goes on the correct carbon, okay? Carbon 2, technically, okay? Now, acid chlorides, we've learned before, react with excess ammonia, excess primary amines, excess secondary amines to give you amides. So for this, we want to draw the amide. Okay, so make sure you keep all your carbons there, and double bond, oxygen, and then just write NH2. Okay. So nitrogen with 3 total bonds has a lone pair, it has an octet, a formal charge of 0. Now in this case, what do we do? Well, that's the acid-catalyzed hydrolysis. So for this one here, we want to draw in our 6-membered ring here, and then we want to go ahead and sketch in the acid, okay? So one way to remember this is that if you have acids, you form the acid, okay? And ammonium is also a weak acid, so NH4 plus is going to be the component, okay? You don't want to draw NH3, all right? Let's go ahead and do the next problem, which is practice number 27 in the textbook. In problem 27, you want to look carefully at the number of carbons. There's 6 carbons in the ring, which doesn't change at all, and we don't increase the number of carbons, so somehow we're going to this primary amine. So once again, you want to do retrosynthesis by thinking backwards. Amines come from amides, okay? And amides come from acid chlorides. So now we kind of played the movie backwards. Let's assemble it in the forwards direction. We would take our acid chloride, okay, and remember, to make an amide, we would add excess ammonia, excess NH3. So this gives you the amide. Once you have the amide, then you want to treat this with LAH to give you the desired target molecule. Now LAH, I never write excess next to the LAH. LAH always requires water as the second step, okay? So you want to make sure you write H2O as step 2. Let's go ahead and try problem 28. Okay, here's problem 28, part A, and it asks us to propose a mechanism for each of the following transformations. So we just have to go through the motions here. So you know, you want to protonate this oxygen, okay, and that gives you the intermediate I'm trying to draw here. Okay, so now we have a really reactive electrophile, and water, which is not a strong nucleophile, will engage this. Okay, now I should mention that a 4-membered ring like this is highly strained, so this is a quite reactive amide. As water attacks, you form a tetrahedral intermediate, and we want to draw out all of the busy work here. So remember, water is H2O, and it comes in with 2 hydrogens, so you need to draw them in there. And then here's where we need to do a bunch of, ooh, I made a mistake here. Let me correctly draw the amide. Okay, so here is where we do a bunch of proton transfers. Okay, so we have water present, so we need to do 2 things. We need to deprotonate this guy here, okay, and that makes the kind of diol here, okay, or hydrate, you know, depending on how you want to call that. But anyways, and now we need to protonate this nitrogen. Okay, so that's a deprotonation. Here's protonation. So what do we protonate with? I would just use H+, okay, it's easier to draw. And you'll make this intermediate down here. So now we have the 2 hydrogens and the formal charge of +1 on there. I'll just draw this bond out here a little bit so it looks a little bit better. And now you can break this bond. Now, when this bond breaks, you actually have a ring opening occurring. Okay? And that's why this nitrogen is way over here and the carbonyl is way over there. So when you eliminate or break that bond, you form a carboxylic acid. And I'll draw it ugly looking, so I'll draw this bond going down, this one coming over here, and I'll draw a line straight up so you can kind of see the square there. Okay, so you kind of form that, and that's basically what we have up here with, you know, two carbons in between a carbonyl and an amine. So this amino acid here, well, that you're trying to form, we need to do two things, remember. We need to deprotonate okay, deprotonate. And then, well, I'll just draw this out as a separate step here. So there we have our carboxylic acid, and carboxylic acids can exist in H3O plus reaction conditions. And remember, the amines are basic, so you want to protonate that guy. P for protonation. And you get, at the end of all of this busy work, your amino acid in the protonated state. Okay? So what do we have? PAD, PED. So that's a PAD-PED, and then a P at the end. Okay? PAD, PED, P. Now let me spend a few moments discussing this. Since we have acid conditions, one way to check all of your work here is to make sure that you don't have any negative charge in any of the structures. Okay? We don't want to see an O with a negative, with one bond to it. We don't want to see anything with two bonds to nitrogen, say for example, and a negative charge on that nitrogen. Okay? Everything must have a formal charge of +1 or 0 as a formal charge. The other thing is that you don't want the whole molecule to ever be +2. Okay? What do I mean by that? Well, look at these last two steps here, okay? I told you that we needed to deprotonate and then protonate the molecule. If we accidentally took this lone pair here and we said, oh yeah, we need to protonate that, I remember that part, and we protonate here, what are we going to form? We are going to form a molecule that has a +2 formal charge, and you don't want to do that. Okay? Such a thing would be just highly acidic and it's not going to form. Okay? So you don't want to form something like this where you have two pluses in the same molecule. The charge of that whole molecule would be +2. So that's all I wanted to mention there. Let's try to do part B now. Here's part B, and I told you that if sodium hydroxide were to react with an amide, it selectively deprotonates and you don't have a reaction. Now, for some reason, this does indeed react, and I told you why. It's because of ring strain, okay? And so we have to propose a mechanism for this, all right? The mechanism I would propose is one that would avoid the use of a -2 charge. So what I want to try to draw is maybe something attacking, instead of acting as a base, okay, hydroxide would act as a nucleophile and attack the carbonyl carbon. Okay. So this highly reactive and unusual substance might do that. And then this negative charge would immediately kick off the amide. Okay, so we have a resonance stabilized carboxylate. We have a highly reactive, very basic, kind of leaving group. But the reason why that terrible leaving group would leave is because the ring strain is relieved in this step. Okay. Kind of like you don't want to go to the library and study, but you can get out of the house where your aunt is visiting and she's starting to get on your nerves or something like that. I don't know. Maybe that's a terrible analogy. We need to do a couple of things here. Actually, we only need to do one thing. Presumably, this is in water, okay? Sodium hydroxide is soluble in water, so I'm going to invent the use of water here. And this guy here will return the proton to the nitrogen, giving me a deprotonated amino acid. Okay, so I'll just draw NH2. Okay. Where is sodium? Sodium is a spectator ion that's in there, so Na plus is all around, and so now it's going to be paired up with that ion. So anyways, that's question 28. That's all I want to show for section 12. Thanks for watching, and please do consider subscribing if at all you find these videos helpful.